This is another Creo webinar. This webinar is being recorded, so I hope that you're able to accept the recording. Good. So today's Creo webinar is entitled Know Thy Star, Know Thy Planet. And where does that title come from? It's actually derived from a piece of literature written by a famous Chinese general named Sun Tzu, who in his book, The Art of War, used a similar turn of phrase with regards to understanding one's adversary. Now, this is not a discussion about adversarial relationships by any means. Indeed, what we're trying to do here is to tell a story about the composition of the Earth and the other planets with respect to the composition of the sun. So when we talk about knowing thy star is knowing thy planet, it gives a clue about not just the composition of our planets in our solar system, but that of planets elsewhere, planets around other stars. So today, what I thought we could do is to spend some time looking at the basis of this idea called Know Thy Star, Know Thy Planet, and where this idea may lead us in the coming decades. So I'm going to begin by sharing with you some images to help me get my point across. So I hope you all can see that this is a picture of a rainbow. The rainbow, of course, is a familiar thing to all of us. On a rainy day, you go outside and you see such a phenomenon when the sunlight is shining through droplets of water suspended in the atmosphere. Cumulatively, these droplets act as a prism. They take sunlight and then they divide the sunlight based on wavelength. So if you can see my cursor here, I'm pointing to an area or highlighting or circling an area where there are the so-called fast rays. These are violet colored light rays. And over at the other end, over here, are the so-called slow rays. These are the infrared, red and deep red rays of light. In optics, researchers have been studying the properties of light and its behavior through substances like water, like air, and other gases, and through transparent substances like glass for a very, very long time. One feature of light that is particularly interesting to those of us who are concerned with the studies of origins of things, like origins of life and origins of planets, is that the light that you see here in this rainbow contains information. And that story is an interesting story that begins with this person, Isaac Newton. Now, this is a statue of Isaac Newton that is found at Cambridge University in England, part of the United Kingdom, in Europe. And Isaac Newton, of course, was a professor at the University of Cambridge, where he performed many experiments, and in particular, gave us Newtonian physics as well as invented the calculus in order for him to be able to engage in his physics calculations. Well, Newton was also very, very interested in light, and he performed experiments using a prism, trying to understand more about light and its properties. Of course, he wrote a famous book about this called The Optics. But this captured the imagination of many scientists around the world at that time, and in particular in Europe, in England, as well as in France and Germany, which were the leading centers of science at that time in the mid to late 18th century. So Newton described how using a prism gives you this information about the colors of light separated from white light. And that is shown here in this diagram. Of course, a beam of white light focused into the prism here is then split into its constituent colors. It's the rainbow. But let's look at the rainbow in a little bit more detail, shall we? And that's something that this person did, Wollaston. Wollaston took a very large prism and in 1802 described an experiment where using this large prism and focusing white light into the prism, he was able to project this rainbow onto a white wall in a room that he was working in. When he did so, he noticed something unusual, that within this rainbow, there were lines, dark lines that looked something like this. So the rainbow projected from the prism from sunlight was discontinuous. Wollaston wrote this up in a paper which he read in 1802, and 10 years later, this person performed an experiment using the largest, most perfect glass prisms of his time. And this person's name was Fraunhofer. Fraunhofer performed these experiments in Germany, in the city of Heidelberg mostly. And he was famous in his day for being the most talented glassmaker in Europe. So he was able to fashion the largest, purest, clearest, most perfect prisms ever before fabricated, where he performed the experiments that were started by Newton and then followed on by Wollaston. When he did that, he found that light from the sun, yes, directed through this prism, led to these dark lines indeed. But then there were many, many, many more lines. All in all, Fraunhofer found dozens of these lines. They have since been come to be called Fraunhofer lines, named after him, and he documented them. That was for sunlight. Fraunhofer then did something remarkable and very scientific. He took light from a candle and then directed its light through the prism. And he found that the pattern of the lines in the spectrum, the rainbow, was different from that of the sun. Then he performed an experiment with a blast furnace, a coal-powered furnace, very bright, and he found that the line pattern from that was different from that of the candle, which was different from that of the sun. So Fraunhofer, with these simple experiments, just with a glass prism and some lenses, was able to show that the power of the sun is not like that of a candle burning or even a very powerful furnace burning, that it was something different. Then Fraunhofer did an amazing thing. He performed an experiment where he took a telescope and gathered the light from a star called Sirius, which is a bright blue star in the sky. And he focused its light through a prism. And he found that the lines from the star Sirius were different from that of the sun. So he was able to show that different stars were different in their compositions. And he didn't really understand what this was. It wasn't until something like 25 or 30 years later that Bunsen and Kirchhoff were able to show that indeed absorption and emission spectra in light from different substances and depended on the elements of those substances. And each element, as shown here, has a different spectrum of absorption and transmission. That leads us to stars. So I've given you a little bit of background on how we've known already for 200 years that different stars are different from one another in their composition. Well, since that time, we've been able to classify stars based on their color. So yes, they differ from one another in composition, usually in trace elements, but they also can be categorized based on how bright they are and their color, which is a function of their temperature. So stars are classified as O, B, A, F, G, K, and M stars. M stars are small. They're the most common stars of our galaxy. They're something like 70% of stars. And they are relatively cool stars. Their temperatures are around 3,000 Kelvin. K stars, which are a bit brighter than M stars, they're about 14% of stars of our galaxy. They're quite a bit hotter. They're about 1,500 degrees hotter, 4,500 Kelvin. G stars, which are roughly about 4% of the stars of our galaxy. And our star is a G star. There are these yellow stars. They're about 5,000 kelvins. Another group of stars, a bit brighter, F stars. They're 7,000 Kelvin. They're yellowish, whitish. Then A stars are very hot indeed, 9,000 Kelvin. And they're white. And then the hotter you go, the bluer you get in these stellar classifications. Also, the hotter you go, the larger the star tends to be, the shorter its lifespan, and the brighter it is, and the rarer it is. How does that relate then to planets? Because I started this conversation with you with the title, Know Thy Star, Know Thy Planet. Well, here is a very simple representation of the sun and the planets of our solar system. This is not to scale because you couldn't put all of this into one figure, right? The sun is enormous in this respect. But I just wanted to show this to you because I want to emphasize that 99.8% of the mass of the solar system is in the sun. So by definition, the composition of the solar system is the composition of the sun. The planets are minor. But because the average composition of the solar system is that of the sun, the planets have a compositional genetic relationship to the sun. So by knowing the composition of the sun, you know something about the composition of the planets. If you know another star has a different composition, then it is likely that planets around that star have a different composition from the planets of our solar system. That is because planets and the stars that they orbit originate out of a cloud of gas and dust in these molecular cloud systems that are in between the spiral arms of our galaxy that coalesce and collapse in their own gravity and form a star at the center, and then matter that orbits the star and gets flattened during that orbit, thanks to the conservation of angular momentum. And we also know separate out frequently into rings. That's what these are. These are called Alma disk rings. Within these rings, there are different reservoirs of material that in turn coalesce to form planets and asteroids and so forth. Knowing thy star means that you know thy planet. A star is most of the composition of its solar system. A planet is a devolatilized star. It's the star minus all of the hydrogen and helium. Most of the sun, just like all the other stars in the universe, is composed of hydrogen and helium. It's about 3/4 hydrogen and about 1/4 helium and a teeny bit of everything else. Planets are made of that teeny bit of everything else. So if you took the sun and removed all the hydrogen and helium and then looked at the relative proportion of the elements, you get the Earth, you get the moon, you get Mercury, Venus, etc. Now, of course, where the planet forms with respect to the sun is important. If you form very close to the star, you form in a hot region that tends to be dry, poor in volatile elements and compounds. Farther away, you tend to form gaseous and icy bodies. Think of a campfire in a cold night. Being very close to the campfire, you're warmed very nicely, but stepping away from it, you get cold quickly. The solar system is like that. Every solar system is like that. We have Earth-like planets, rocky metal worlds close to the star, gaseous and icy planets farther away from the star. In 1995, these two gentlemen described the first extrasolar planet. This is Michel Mayor here on the right and Didier Queloz here on the left. They found a very large planet in a close orbit around its star. This planet was many times the mass of Jupiter, and its year was only about 4.5 of our days. So it was whipping around its star. Very unusual planet. They were able to detect this planet, and it was repeatedly verified, thanks to the fact that the planet was so close to its star and it was so massive that it was actually tugging and deforming the star. So they could see that the spectrum of the star was changing, was moving, because the entire star itself was deforming and moving. Since that time, many thousands of extrasolar planets have been discovered. Just a few weeks ago, we reached the 5,200 mark for the number of extrasolar planets, planets around other stars. This diagram here, which is originally from Michael Hart, who, by the way, took it from Maunder in 1913, who got the idea from Isaac Newton's Principia Naturale, published in 1704. The idea that there is a zone where the distance from the star is just right, so it's neither too hot nor too cold, where the climate is good for life, for living. And that's a so-called habitable zone. So the habitable zone here in this diagram is the distance from the star whereupon on a planetary body, water would remain stable. As you can see, when you go towards hotter and hotter stars over here, the habitable zone is different. So habitable zones could be really, really far away from a very, very hot star because you can't be too close. It's just too hot. And for a very, very cool star, it has to be closer in. So what really matters here is that we have found over 5,000 extrasolar planets. We know something about their size, their radius, and we know something about their density. And that's what this figure is here from this past November. Here on this axis is density. And here on the x-axis here is radius and Earth radii. So Earth here is at 1. Earth is 1 Earth radius. And Earth's density is just about here, where that little square is that I'm circling. So we're here. But there are extrasolar planets that are very similar to Earth's radius and density. Look, they're over here. They're a little bit smaller, but they have kind of the same density of Earth, which implies that they have more or less Earth's composition. But then there are planets which have Earth's radius, but are much denser. They're way up over here. These planets are probably mostly composed of metal with a very thin layer of rock. There are some other planets, like this one down here. It's about, well, a little bit larger than that of Mars, and it has very low density. In fact, its density is lower than that of average rock. So it's probably mostly composed of rock and atmosphere with very little metal. There is physics and there is chemistry in diagrams like this, because you can also see as you go up in size, density tends to go down until you reach something around 10 Earth radii, and then the entire system changes. You get a new kind of planet. You get planets that can have Earth densities or greater and be very, very large. These unusual planets are called sub-Neptunes, and these sub-Neptunes and another category of planet here called super-Earths are the most common planets in our galaxy, and they are not represented in our solar system. So our solar system seems to be a 1%er. It's not in the general category of solar systems that have super-Earths and sub-Neptunes. Super-Earths are very low densities and sub-Neptunes of relatively high densities. That trend is real. And it's new. This is new science that we have to understand the physics and chemistry of. And the way we're going to do that is by taking the composition of the stars that these planets orbit and devolatilizing them. Take out the hydrogen and helium, look at the composition that's left behind, and then compute what the likely compositions are of these thousands of planets that are out there. Are they like Jupiter, like what we have in our solar system, or are they something entirely different? There are planets like this one, WASP 76b, that may be the only planet in their system. This planet is something like the mass of Jupiter, but it has a year that is only about 2 days, and it goes around a star that is even more massive than our star. How do we know about this planet? It's going to be by taking the composition of its star, and if we're lucky, we can maybe get the composition of its atmosphere, because this planet is so close to its star that its atmosphere is 2,500 Kelvin. It's getting close to the temperature of an M star. So the future of understanding and making sense of the origins of planets, which are ultimately the origins of habitats for life, is to know the star. Feel free to write me questions by email through the Creo web interface, and we can continue these discussions. And I look forward to seeing you again next time at another one of our live webinars.